Hello, we are Team 6 formed by Alberto Mejia, Elizabeth Ambris, and Karen Zarza. And we are going to project our challenge, which is to construct an electric motor, which is a machine that transforms electrical energy into mechanical energy, and it takes advantage of the fact that when a conductor through which an electric current circulates is within the action of a magnetic field, it tends to move perpendicular to the lines of action of the said magnetic field.
Well, the concepts that we use in this project are Ampere's law, Maxwell equation, Faraday's law, torque, magnetic field, electromagnetics, Lorentz force, and Biot-Savart law. Well, the materials of our electromagnetic motor, we use 1 meter of copper wire with a caliber of 22 millimeters, 2 batteries of 1.5 volts, 2 magnets, 2 cables of copper with a caliber of 40 millimeters, and 2 connectors. When the current flows through the loop, a magnetic force is exerted on each conductor, which following the Lorentz law is perpendicular to the plane formed the magnetic field and the conductor. One of the two conductors are parallel to the magnetic field lines, the force is 0, and the conductors perpendicular to the lines, the force causes the turn of the loop, bringing it into the vertical position, where the magnetic field that produces the loop is aligned with the magnetic field of the magnet. If the current were to be maintained since the loop passed through that position, the torque will opposite the rotation. For this reason, the current is transferred from the external circuit to the loop using a switch formed by 2 metal sheets in the shape of the half moon called tin. The ends of the loop of brush make the contact first with the tin and then with the other, which causes that while the current through the external circuit always has the same direction, the current in the loop reverses in the direction of the circulation every half cycle. Thus, the torque always drives the rotation.
Well, the first thing that we did to obtain the torque is to calculate the value of the generated magnetic field with the solenoid formula, since we are working with loops, where we used mu0 n for the number of loops, I for the current, and L for the wire length. For the current, we used a value of 0.001 ohms for the resistance of each battery. We decide this because that's the internal resistance a brand new AA battery has. Substituting these values, we obtained the magnetic field was 0.02168 Teslas. Once we have our magnetic field value, we can now calculate the torque with the next formula. And well, we got that the result for the torque was 0.01597 newtons per meter. And next, to see if our magnetic field was correct, we used a simulator to using the values of our magnet. And from this simulator, we obtained that the value of the magnetic field is 215 Gauss, which is 0.0215 Teslas, which is the same one as the one we get in the analytic way. And we also obtain a diagram of how the magnetic field is manifested in this specific case of the project. Also, we can see how the scale of Gauss is represented in the different areas of the magnetic field.
To create the MATLAB program that simulates this situation, we use the solenoid formula and use the theta as a independent variable. And with this, we could see the maximum torque and the minimum torque. To obtain the torque design, we use the formula torque equals power over angular speed, and obtaining the angular speed with the revolutions per minute and the power with the volts and amperes of the batteries. In substituting all this value, we obtained that the experimental torque was 0.00159 newtons per meter. Comparing these results, we can see that the experimental value is 10% smaller than the value obtained in the theory.
And well, for the conclusions, we got that an internal resistance has its origins in resistance losses in the electrolyte during the transformation of energy. Alkaline batteries have a relatively small internal resistance depending on the time of use. The resistance in a 1.5 volt AA battery initially has a very low resistance, but over the time passes, it increases to approximately 1 ohm as its use continues. So knowing that we can infer that at the moment of the experiment, the battery was new when we were doing the experiment, the resistance value at the beginning was very low. But the more we tried, the resistance value increased as time passed. The magnetic field decreases as well as the torque. On the other hand, we did not take into consideration these increases because of the resistance. We only established a constant value to obtain the torque, and that's why the experimental value is 10% smaller than the value obtained in the theory because of the decrease of current in the batteries when making the experiment.